Hello, this is Dr. Gardner. Today we're going to look at how to draw Lewis structures for molecular compounds. Now you need a few skills before you start this video. First of all, you should already know how to write electron configurations and predict your number of valence electrons that you have in each of the atoms we will be using for our Lewis structures. I also expect that you've already practiced drawing Lewis structures with ionic compounds, but today we're going to look at molecular compounds where we're sharing electrons in covalent bonds as we've described before. Now realize if we're drawing a Lewis structure for a molecular compound, when we show a covalent bond, we will indicate that with a single line where two valence electrons are being used for the covalent bond, or if we have a double bond, we'll show two lines where four valence electrons are used, or we'll show for a triple bond three lines where six valence electrons are used. So in this circumstance today then was the only time with molecular compounds where we'll use lines between the atoms. Never connect ions with lines in our Lewis structures because that would indicate a covalent bond where we only have ionic attractions. So be very cautious there. So what we're going to be first looking at is I'm going to cover some of the steps that we're following as we write Lewis structures, and then I'm going to give you some helpful hints and tips for things we look for when we're drawing Lewis structures to make it a little bit easier for ourselves. And then we're going to look at common atoms and the types of bonds we'll see to those atoms in Lewis structures. For example, we'll look at carbon and hydrogen and then several other types of elements. And then we'll practice drawing several Lewis structures together with all the steps we've described. Okay, so first of all, the very first thing you should do when you're drawing Lewis structures is take all the atoms involved in the formula of the compound and write an atomic skeleton. So sometimes we'll say this is a skeletal structure. When we're doing this, there's a few things you might recognize to help you start. First of all, you might realize that atoms are often arranged symmetrically. Okay, so for example, if I have carbon tetrafluoride, and if I'm considering the symmetric relationship there, well, maybe I have carbon with fluorines bonded to it. So let's put the fluorines, there's four of them, let's put one per side. So that would be nice and symmetrical, wouldn't it? Okay, so we go ahead and show all of our fluorines. And after we show our fluorines, if we're going to go ahead and put a skeletal structure, we're going to assume they're connected by at least single bonds. So I could go ahead and put single bonds in here. Now I would have counted up my valence electrons and also placed those as lone pairs. And I'll show that in greater detail coming up shortly. But after I've drawn that, that gives me a skeletal structure to get started. Okay, so that's a very good start there. Now, I should also realize that often in my formulas, the first atom may be the middle one, and usually when the second atom, there's several more of that atom, like I have four fluorines here. Usually the element with the greatest number of atoms is on the outside, and the one with the fewest number of atoms is often in the center. So that's frequently something we can try to attempt at least to start to draw Lewis structures. Now, when I have finished drawing the carbon tetrafluoride Lewis structure would look something like this. Now we will be practicing them all the way through from scratch, but I just wanted to see the symmetrical arrangement here. Now, sometimes the chemical formula we're given may also provide clues to the structure. For example, if I consider acetic acid, which is a component in vinegar, acetic acid can be written, one of the ways we might write it is CH3COOH. When I write acetic acid's formula this way, there's some hints about what the Lewis structure might look like from the chemical formula. In fact, when I see carbon followed by the three hydrogens here, that's often a hint that when I draw the skeletal structure, I'll have a carbon and three hydrogens shown. So those three hydrogens that I saw in my formula right here are hinted at being bonded to the carbon before them. So we can try to draw our skeletal structure with three bonds to those hydrogens, and then the next carbon could potentially be bonded to that first carbon. Now that fills the first carbon with a full octet, so that looks like a pretty good structure. And then maybe I have oxygen bonded to this carbon. And I have a second oxygen, so maybe it's also bonded to that carbon. And perhaps we have, in some circumstances, a hydrogen bonded in the last position. So we might have a hydrogen bonded here. Okay. Now, this carbon does not have a full octet, so we'd see we actually have a double bond here. And if we show our lone pairs, we'd have one here, one here, one here, one here, and here we'd have lone pairs on these oxygens. So we can see there's a lot of hints. These oxygens are bonded to the carbon before them. Okay, this hydrogen is bonded to the oxygen before it, and those hydrogens were bonded to the carbon before it, so there can often be some hints from the structure, from the chemical formula concerning the structure. Okay, so I just wanted you to see that. Now, first of all, let's think about this. So we're writing this atomic skeleton out. A lot of times the central atom that I'm picking would also be the atom I predict to form the most bonds. So carbon's a good choice. Nitrogen can be a good choice. Nitrogen and oxygen can be good choices. So those are all good atoms to put in the center. Now, however, if I have fluorine or hydrogens tend to only form one bond, so they'd be good outer atoms. So for example, if I'm looking at methane, I might go ahead and put the carbon in the center and have 4 hydrogens bonded to it. Okay, so the carbon, which tends to form more bonds, I'm putting in the center of my Lewis structure. So that's a good way I might try to draw my skeletal structure. Now, frequently the center atom also tends to be the least electronegative. However, we actually broke that rule with the methane structure. The hydrogens are the least electronegative, but the reason they went on the outside is because they can only form one bond. So they'd be a very poor choice to be in the center since they could only bond to one other atom. Okay. In other cases, though, the central atom is very likely to be the least electronegative if it can form multiple bonds. We would put that one in the center in that case. So we'll see some cases of that here in a little bit. Just remember, hydrogens, though, are generally on the outside. So that happens to the hydrogens being on the outside trumps the rule to put the least electronegative atom in the center. So that's something important to remember. Okay, now the second step, once you've drawn a skeletal structure out, we'll want to go ahead and add up all of your valence electrons and see how many we have to put in present in any lone pairs, non-bonding pairs of electrons in our structure. Also, you should realize that there's a couple of things you have to consider when you're adding the valence electrons. If you have an ion, the number of valence electrons you should be using could be altered from the number that were on the neutral atoms you are beginning with. So, for example, if you have a cation, the cation indicates that you've lost one or more electrons. So I should subtract the number of electrons equivalent to the charge on the cation from the total valence electrons that I'm adding up to build the Lewis structure out of. Now, if I have an anion, on the other hand, though, how negative that charge is, the magnitude of the negative charge determines how many electrons were gained by that anion. So the anion must have gained one or more electrons. So I'd have to add those to the total for the sum of the valence electrons. So you want to correct for that, or you'll have the incorrect number of valence electrons when you're building your structure. Now, the final type of Lewis structure we'll be looking at in some cases for cations and anions that are more complex are when we have polyatomic ions. Now, polyatomic ions frequently will have multiple non-metal atoms that are covalently bonded together within the polyatomic ion. However, as a group, that group of atoms will have gained or lost electrons to have an overall charge. To indicate that charge belongs to that group of atoms, we're going to go ahead and put a square bracket around the formula, the Lewis structure of the ion, and then we'll show the charge in the upper right hand side of the brackets as a superscript. So for example, if I have the ammonium cation, I have nitrogen in the center and 4 hydrogens on the outside. I put square brackets around that and indicate the positive charge on the ammonium cation in the upper right hand superscript. Now if I have an anion, let's say we have the carbonate anion, you might have come up with a Lewis structure that looked like this. Carbon in the center, 3 oxygens on the exterior, we have a double bond in there. We put square brackets around the oxo anion here, and we show the charge in the upper right hand corner as a 2- for carbonate. And so I need to make sure I use those brackets and indicate the charge because they will show why we built the structure with, in ammonium's case, 1 less electron, and in the carbonate's case, 2 extra electrons. So that's helping us keep track of these and representing the polyatomic ions very efficiently. Now for step 3. When we're placing our bonds between each of the bonded atoms, we'll often start with a single bond. Each line we show represents 2 electrons being used in that Lewis structure. Now, however, for step 4, you might have extra electrons to place after you put a single bond between each of the bonded atoms. If you have extra electrons, we normally will place those on the more electronegative atoms. Those more electronegative atoms are frequently on the outside, so I start to put extra electrons on the outer atoms in the Lewis structure rather than the central atom. As I fill up the valence shell of those outer atoms till I give them usually an octet for most cases, we're going to go ahead at that point and see if we've used all the electrons we have. Okay. Now, a few things to remember, though, when I'm placing extra electrons. Hydrogen atoms in my Lewis structure should only have 2 electrons when bonded, so don't try to give them any more than the first 2 they need for that first bond. Okay. Any element in the second period, such as carbon, nitrogen, oxygen, okay, fluorine, they tend to want to have a full octet, meaning 8 electrons around them to provide stability. So all the period 2 elements, we predict 8 electrons in the molecular Lewis structures around those species. If you do not have 8 and you can draw a better Lewis structure that contains 8 around those atoms, then you should try to do so. Now, below period 2, if I look at period 3 through 7, over on the right-hand side of the periodic table where we said we have the p block, where the electron configuration is filling in the p subshell, we would expect many times to have 8 electrons around those atoms, but as we start to be closer to the d orbitals, for example, as we go up in energy, as we put more electrons on the atoms in these periods, we can sometimes have what we call an expanded octet. So we can sometimes have more than 8 electrons around some of those elements. So sometimes you'll see them with 10 or 12. But I would never expect to see 10 or 12 electrons around period 1 or 2 elements. So this is only period 3 and below. As I said, though, frequently we'll also run into compounds, though, where we kept following the octet rule. Okay, but just be aware, sometimes we might break the octet rule. Now, step 5 is to make sure you've used the right number of electrons in your structure. If you have too few electrons to fill the outer octets of the atoms in your Lewis structure, what you want to do is share additional electrons in covalent bonds until all of the atoms in your structure have the full number of electrons they need to fill their octets. Now, since we gave the outer atoms, the more electronegative atoms, their electrons first, frequently they have the extra electrons and the central atom may be deficient. So in that case, we may want to make a double or a triple bond to the central atom by taking some of the electrons in lone pairs from the outer atoms and moving them into a bond to the central atom. So if you have too few electrons to fill the octet, start putting double and triple bonds in your structure, in a brief summary there. Now that we've covered the rules as we're going through these structures, let's go ahead and consider some helpful hints that'll help you correctly draw many types of structures. If I have a neutral atom that I'm using in my molecule, I can often predict the number of bonds it might form. The number of bonds that neutral atom will frequently form is often the same as the number of additional electrons that it would need to fill its valence shell. So for my period 2 elements, usually I need to have 8 electrons total. And so if I have, let's say, nitrogen, so if I'm thinking about nitrogen for just a second, if I think about the Lewis structure for a nitrogen atom, it has 1, 2, 3, 4, 5 electrons. However, if it would like 8, a full octet, we can take 8 minus 5. We predict it needs 3 more electrons, so it may form 3 bonds in many structures. Okay. Now, this could be 3 single bonds, or I could have a double bond, which counts as 2 of the bonds, and 1 single bond. Okay, but in any combination of multiple bonds, could be a triple bond, a double bond, and a single bond, or 3 single bonds. Those would all be situations that would satisfy this prediction of 3 bonds to nitrogen. So basically, we're saying we have an orbital here, half filled with 1 electron that can form a bond. We have an orbital here, half filled with 1 electron that can form a bond, and an orbital here, half filled with 1 electron that can fill a bond. So that helps us make some general predictions to get started. This also shows us why carbon, if we look at carbon, which has 4 valence electrons, and would need 4 more to fill those 4 half-filled orbitals, would often form 4 bonds. Okay, so that helps us make some really useful predictions. Now, atoms that can only make 1 bond. This tends to be hydrogen and fluorine. Those types of atoms that we predict only to want 1 more electron to fill their outer valence shell. Hydrogen only needs 1 to get to 2, and fluorine only needs 1 more to get to an octet. Those tend to be on the outsides of my Lewis structure rather than in the center, because the central atom we frequently want to show multiple bonds to. Okay, so hydrogens and fluorine is usually on the outside. Now, also, we can consider, after we think about hydrogen and fluorine on the outside, usually the least electronegative atom, the atom that's drawing electron density towards itself the weakest, it tends to be in the center of my Lewis structure. Okay, so it kind of makes sense that I put fluorine on the outside. Not only does it only form one bond, it's also very electronegative, so it should be on the outside. However, be cautious, because even though hydrogen has a very low electronegativity and might meet the rule for the least electronegative atom, since it only forms one bond, it's a very poor choice to put in the center. We want it on the outside. Okay. Here's some other hints for drawing Lewis structures. If you'd like to do a very quick calculation of how many bonds maybe you should have in your Lewis structures, well, you can predict the number of bonds that maybe be present by counting the number of electrons you have and compare that to the number of electrons all of your atoms would like to fill their valence shells. So, for example, if we consider methane, CH4. If we consider methane, well, we have a carbon. Okay, the carbon has 4 valence electrons, but it would like 8. Okay, so it really would like 8 rather than just the 4. So it would like to get to 8 for its number of valence electrons, if it could have them all. Now, if I look at the hydrogens, well, there's 4 of those. Now, each one of those hydrogens has 1 valence electron. So if I take 4 times the 1 of each of them, I have 4 electrons total. Now, each one of those hydrogens would like 2 to fill its s subshell. So really, combined, we want 2 per hydrogen times the 4 hydrogens. We want 8 there. Okay, so I can basically say that I would like to have a total, if I could, of 16 valence electrons to fill all their outer valence shells. If they were allowed to have that many, they actually only have 8. Okay, so they actually only have 8. So if I use this equation I've given you, the electrons that are wanted are the 16 that we just determined, and the number of electrons that we actually have is 8. Okay, so that gives me a value here, first of all, of 8 more electrons needed to fill those valence shells. If I divide that value by 2, that can predict the number of bonds I might have on my structure. So 8 divided by 2 predicts 4 bonds are likely to be in the structure. Now, if I look at the Lewis structure for methane, we have carbon in the center, and we have 1 hydrogen bonded with a single bond. We have a second hydrogen bonded with a single bond. We have a third hydrogen bonded with a single bond, and we have a fourth hydrogen bonded with a single bond. So we have 4 single bonds, just as we made with our brief prediction. Now, frankly, I won't need to do this calculation, but you might find it kind of useful if you would like to try to predict numbers of bonds in your structures in advance. Okay. Now, if I need to add electrons to my structure, because let's say I haven't used them all yet, we normally will put them on the most electronegative atoms first. Now, those tend to be the atoms in most cases on the outsides of the Lewis structure. If I have any more electrons beyond that, we'll place them on the central atom after the octets of the outer, more electronegative atoms are filled first. Okay? Now, if you find that you need to remove some electrons because you've put too many in your Lewis structure, well, take them away from the least electronegative atom first. So usually take them away from the central atom first before you take them away from the more electronegative atoms. Now, if I have found I don't have enough electrons to fill all of the outer valence shells for my atoms, we often will start to share additional electrons by moving some lone pairs into double or triple bonds, as I've mentioned before. Okay. The next thing you should realize is if I'm trying to draw multiple bonds, I shouldn't try to draw more than a triple bond between 2 atoms. So if I, for example, I have 2 carbon atoms, well, we could go ahead and show a triple bond between those carbons, but I wouldn't try to draw a quadruple bond. Any additional electrons needed to fill the octets for these carbons would have to come from another source. Perhaps some hydrogens could do the trick for us. Okay. So hopefully you find these tips kind of useful. I want to show you some common atoms that are present in Lewis structures. First of all, often we'll have hydrogen in Lewis structures, and if we're considering that case, hydrogen only needs 2 electrons to fill its valence shell. However, most other atoms that we're going to be using in our Lewis structures today will want a full octet of 8 electrons. Okay, in that case, we're going to have a combination of bonds and lone pairs to fill that valence shell. Okay. Now there are a few exceptions to the octet rule. Sometimes you can have an incomplete octet in some circumstances. For example, if you have a free radicals tend to have an odd number of electrons, so there often is an orbital that's only half filled with one electron. But free radicals are very reactive, so oftentimes you'll hear people talk about taking antioxidants for their health because they tend to react with the free radicals before they damage other molecules in your body by reacting with them. Now, if we consider atoms such as carbon and silicon in that carbon group, they tend to have 4 bonds and no lone pairs on those atoms. So there's several different ways I could write this. The 4 bonds could be represented as 4 single bonds to a carbon, or I could have a double bond and 2 single bonds, or I could have carbon with 2 double bonds to it, or I could have carbon with a single bond and a triple bond. So as long as I have 4 lines to my carbon in the form of any single, double, or triple bonds that all add up to 4 bonds total and no lone pairs, those are very good predictions for potential structures in your Lewis structures. Okay. Now, if I consider the nitrogen group, like nitrogen and phosphorus, they tend to have 3 bonds in their structure and 1 lone pair. So I might see nitrogen with a lone pair and 3 single bonds. I might see a lone pair and a single bond and a double bond. Or I might see a lone pair and a triple bond. So those are common structures for nitrogen. If we consider oxygen or sulfur, my oxygen group, they tend to have 2 bonds to those structures and 2 lone pairs. So for example, I might see oxygen with 2 lone pairs and 2 single bonds, or I might see oxygen with 2 lone pairs and a double bond to meet this requirement. Okay, so you may have seen, for example, this first structure with water, H2O, as we have the 2 extra hydrogens bonded as those single bonds. Okay, so those are structures that are common. As I said before, fluorine and hydrogen tend to be on the outsides of your molecules. So you tend to see fluorine with a single bond to the central atom, or hydrogen with a single bond to the central atom. Now, fluorine will have 3 lone pairs, whereas hydrogen does not need any lone pairs to fill its 1s subshell. In fact, as soon as I form that single bond and it has 2 electrons associated with that hydrogen, we now will have the same electron configuration as helium and provide quite a bit of stability. So let's try drawing some Lewis structures for different molecules and ions using the techniques we've been discussing. So let's start with methane. So if I want to draw the Lewis structure for methane, well, first of all, I'm going to start with my skeletal structure. So my skeletal structure will choose usually the least electronegative atom to put in the center, but remember I warned you hydrogens only can form 1 bond, so they're going to end up trumping that rule and being on the outside of my Lewis structure. So I'm going to put carbon in the center. I'm predicting quite a bit of symmetry, so I'm going to put hydrogens on the outside. Okay, and I'm going to predict at least a single bond to each one of these hydrogens in my skeletal structure. So I'm going to put a single bond here, 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 and here. And that would indicate a possible skeletal structure, but I need to see if I've used all my electrons yet. So it's a good idea to put together a little table to keep track of the number of valence electrons you have. So first of all, let's go ahead and list our atoms we have. So we have carbon atoms, and we have hydrogen atoms in my structure. Now I want to keep a track of how many I have of each. So I have 1 carbon atom, and I have 4 hydrogen atoms. And then if I consider the number of valence electrons that carbon has, it has 4 valence electrons. So I have 4 valence electrons. If I multiply that by the number of carbon atoms, which is just 1 in this case, I have 4 valence electrons from all the carbons in the structure. And if I look at hydrogen, well, every hydrogen atom has 1 valence electron. But since I have 4 hydrogens, I multiply that by 1, I get 4 valence electrons from all of the hydrogens. Add those up, I get a total of 8 valence electrons. Okay, so I have 8 valence electrons to build that structure with. Let's count how many I've used in the skeletal structure. So each one of these single lines, the single covalent bonds, contains 2 electrons, 1 from each of the atoms, the carbon and the hydrogen, to form a covalent bond. So there's 1, 2, 3, 4, 5, 6, 7, 8. So I've used all 8 electrons, so I'm actually done with this structure. This one was pretty quick and straightforward. Let's consider some other situations. Let's try to draw the Lewis structure for methanol, which is also known as wood alcohol. It's quite toxic. It metabolizes in the body to form formaldehyde, which attach your optic nerves and can cause death if you consume very much of it, so you want to be very careful with methanol. If we consider methanol structure, let's go ahead and draw a skeletal structure. Now, the formula might give me some hints. Like these 3 hydrogens, I predict to be bonded to that carbon. So I'm going to put carbon in the center and hydrogen on the outsides are a good idea. Carbon's also less electronegative than oxygen, so I thought it was good to start with it first in the center. Now, since I only have 3 hydrogens, there's one more bond we expect that carbon would probably make, because we said it should have 4. And since it can't form a double bond to a hydrogen, it's going to be bonded to another atom in the structure. It's a good idea to look to the next atom to the right, so that's probably oxygen that's bonded to next. Okay, and the last hydrogen is usually bonded to the atom before it, so we expect that we're going to have oxygen bonded to a hydrogen here. Now let's go ahead and set up our table to count our number of valence electrons after we have the skeletal structure. So I have 1 carbon atom in my structure, I have 4 hydrogen atoms in my structure, and I have 1 oxygen atom in my structure. Now carbon has 4 valence electrons, and every hydrogen has 1 valence electron, and every oxygen has 6 valence electrons. So if I take the number of atoms times the valence electrons on that type of atom, we get the total number of valence electrons contributed by that type element in the molecule we're looking at. So I have 1 carbon atom times 4 valence electrons. There's 4 valence electrons from the carbons in the structure. I have 4 hydrogen atoms with 1 valence electron each, so if I multiply those, 4 times 1, I get 4 valence electrons in my structure. And if I consider that I have 1 oxygen times the 6 valence electrons that I was given for oxygen, then I have 6 there, so I can go ahead and add these up, and I can see that I have 4 plus 6 is 10, plus another 4 is going to be my 14 electrons here to build the structure out of. Let's see how many I've used so far with my skeletal structure. Each single bond is 2 electrons, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So far I've only used 10 valence electrons. Okay, so what I want to do then is subtract the number of valence electrons used from the total I had. So if I subtract 10 from 14, we're going to go ahead and see that we have 4 valence electrons left to use in our structure. So what I do is that I look at the elements I have, and usually it's it's usually the most electronegative atoms that get the extra electrons first to fill their valence shells. Now the most electronegative atom in this structure is oxygen. So I want to put the extra electrons on the oxygen until I fill its octet. So now oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Each of the hydrogens only want 2 valence electrons, and they have 2 due to the single bonds. Carbon wants 8 valence electrons to fill its octet as well, but right now it has 1, 2, 3, 4, 5, 6, 7, 8, so it's good to go. So this would be my final structure that I would submit as my answer to this problem. Okay. Let's try writing the Lewis structure of phosphorus trifluoride. Okay, so the least electronegative atom in here is phosphorus. Fluorine is the most electronegative atom on the periodic table, so we put the least electronegative in the center here. Plus, remember, phosphorus atoms only like to form or fluorine atoms only want to form a single bond, so fluorine should be on the outside. Okay, so I put phosphorus there. I try to write my structure with a little bit of symmetry, so I have my 3 fluorines, and then as we're looking at the structure, we probably have at least a single bond from each of the fluorines to the phosphorus, so there's going to be my skeletal structure. Now let's set up our table. We have 1 phosphorus atom, and we have 3 fluorine atoms. Now how many valence electrons does phosphorus have? Okay, so hopefully you said that it has 5 valence electrons. Now, how many valence electrons does fluorine have? Hopefully you said 7. Your noble gases are to the right. The halogens each have 7 valence electrons. I would like 1 more. Okay, so if I take 1 phosphorus times its 5 valence electrons, I have 5 valence electrons from all the phosphorus atoms. If I take the 7 valence electrons for each fluorine times the 3 I have, I'm going to go ahead and have 21 valence electrons for all of the fluorine atoms. Whoops, 21. So if I add these up, I have a total here of 26 valence electrons to build my structure out of. Let's see how many I've used so far. 1, 2, 3, 4, 5, 6. I've only used 6 valence electrons so far. So that tells me I still have 20 valence electrons to build my structure out of. Okay. Now where shall we put these extra electrons? Remember, the extra electrons we should start to place on the more electronegative atoms. That's going to be the fluorines, so often the outer atoms, until we fill their valence shell. So the fluorines, I'm going to go ahead and fill them up. Now each fluorine would like a full octet, so they would love to have 3 lone pairs each. Okay, so we have a lone pair on this side of this fluorine here, here, that would give it a full octet, right? Which is what we're aiming for. So I'm going to go ahead and give a full octet to this fluorine and see how many I use. And a full octet to this fluorine and see how many I use, and a full octet to this fluorine. And what I'm going to see then is that I have a total of 8 valence electrons around the first fluorine, then another 8, so that's 16, and then my last 8 around the last fluorine is going to go ahead and give me 24. So since I've used 24 valence electrons at this point, if I subtract that from the 26 I had to begin with, I still have 2 valence electrons to find homes for. If I have extra electrons, let's go ahead and give them to the central atom. So we put them on the central atom, the phosphorus. Now that's a good thing because phosphorus has a full octet. It was not very stable before when it only had 6 valence electrons around it. So since every one of these 4 atoms has a full valence shell, has a full octet, we're going to say this looks like a good Lewis structure. So that would be my final answer for this problem. Okay, let's consider drawing a Lewis structure for ethane, which is a hydrocarbon. It has the formula C2H6. So if I draw a skeletal structure for that, I'm going to go ahead and put the carbons in the center because hydrogens are a good choice to put on the outsides. And I'm going to go ahead and have 6 hydrogens. So I'm going to go ahead and give 3 hydrogens to the first carbon. And I stop at that point. The reason I stop is because that carbon would have a full octet around it. 1, 2, 3, 4, 5, 6, 7, 8. So I've completed its octet. I don't want to put any more electrons around it. So I go ahead and take the last 3 hydrogens and I put them around the second hydrogen. Or second carbon, I meant to say. So now we've used all 6 hydrogens, and carbons have a full octet. All the hydrogens have a full duet of 2 electrons. If I add up all of the electrons I had in the structure, since I had 2 carbons and 6 hydrogens, and since each carbon has 4 valence electrons to build my structure out of, 4 times 2 is going to be 8, so there's my 8 valence electrons. And then if I look at my hydrogens, there's 1 valence electron each times the 6 that I have. I have 6 valence electrons from all the hydrogens. If I add those up, I have a total of 14 valence electrons here. And if I see how many I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 2 per single bond. So I've used all my valence electrons, so it looks like I'm done. So that would be my final answer. Now let's say we're looking at ethene. Now ENE has a specific meaning, but I'm going to tell you that in just a moment. So let's look at the formula, C2H4. If I look at C2H4, I predict that I should put the carbons in the center. So I'm going to go ahead and put my carbons in the center, and then I have 4 hydrogens to find places for bonding. So I'm going to go ahead and bond 2 of the hydrogens to the first carbon, and I'm going to try to make this quite symmetrical. So I'm going to give the other 2 hydrogens to the second carbon. So we go ahead and have a Lewis structure here with 2 carbons and 4 hydrogens, but I can already tell with this skeletal structure that I'm not done with the Lewis structure because the carbons have incomplete octets. So why don't we count the number of valence electrons I have to build my structure out of? And what I'll find is since I have 2 carbons and there's 4 valence electrons for every carbon to build the structure out of, I can take 2 times 4, gives me a total of 8 valence electrons from all the carbons, and I have 4 hydrogens times 1 valence electron from the hydrogen. So I have 4 total valence electrons from all the hydrogens involved. So if I look at this, I have 12 valence electrons to build my structure out of. Let's see how many I've used so far. So I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've used 10 so far. So I only have 2 more valence electrons, right, to build my structure out of. So that's problematic, because if I were just to put a lone pair on one carbon, it would have a full octet, but the other carbon would have an incomplete octet. And if I chose the other carbon to put the lone pair on, well, it's the same problem. One has an octet, the other one does not. So when I have a situation where there's too few electrons to fill all of the valence shells by putting lone pairs, we need some multiple bonds. Now, since hydrogens don't want to have double or triple bonds to them because they only need 2 electrons, so they're very satisfied at this point, we probably should put the multiple bond between the carbons. So why don't we try putting a double bond between the 2 carbons? That would require our last 2 electrons that we had. Now, if I look at this, every carbon in the structure has a full octet. 1, 2, 3, 4, 5, 6, 7, 8. The other carbon also has 8 amongst all of its bonds. So remember, a double bond, those two lines represent a total of 4 electrons. 2 electrons per covalent bond line shown. Okay, so since I've used all of my electrons and everybody has a full valence shell, either octets or duets, we would say this is a good final answer. Oh, I almost forgot to tell you, if you see the ending ENE, well, sometimes we talk about carbon and hydrogen-containing compounds that have the ENE name as a group are called alkenes, and they tend to have double bonds in their structure, so this wasn't surprising. Now let's say we have ethine. So we have 2 carbons and 2 hydrogens. So if I draw the skeletal structure, I have 2 carbons bonded together, and there's 1 hydrogen. Let's make this nice and symmetrical. Let's give each of the carbons 1 hydrogen. Okay, so there's my skeletal structure to get started. Since I have 2 carbons, and there's 4 valence electrons for these 2 carbons, so I get a total of 8 valence electrons from the carbons. And we have 2 hydrogens, and there's 1 valence electron for each hydrogen. We'll see that we have a total here of 10 valence electrons to build my structure out of. Okay, so if I go ahead and build the structure with the 10, well, so far I've used 1, 2, 3, 4, 5, 6, right? So I've used 6 electrons in the bonds I've shown so far. So I have 4 electrons left to build my structure out of. If I try to put extra lone pairs on the first carbon to fill its octet, I could put 4 more there and I would have a full octet, but then the other carbon would be deficient. Okay, and if I put 1 lone pair on each, we still would only have 6 electrons around each of those carbons. We still wouldn't have a full octet. So when you have too few electrons to fill every one's octet that needs an octet, we go ahead and put some multiple bonds. Now if I put a double bond in here, so far I've used 1, 2, 3, 4, 5, 6, 7, 8 electrons, but I had 10 to use, so I have 2 more. So why don't we put a triple bond in there? So if I put a triple bond, now the carbons have a full octet. There's 1, 2, 3, 4, 5, 6, 7, 8 electrons used around each of the carbons. Remember, a triple bond represents a total of 6 electrons. So single bonds are 2 electrons. Double bonds consist of 4 shared electrons in the covalent bonding between those 2 atoms. If we have a triple bond, this represents 6 valence electrons shared between the atoms in bonding. So that's a good thing to remember, but I can count it up readily by looking at the number of lines in my structure. Now, let's consider formaldehyde. Remember I said methanol metabolizes formaldehyde, but formaldehyde in the past has been used to preserve biological specimens. It's a very common species. They use formaldehyde, for example, to also make wood products that in our society from wood side products. Okay, so formaldehyde is very common out there in industry. If I look at the structure for formaldehyde, well, the skeletal structure, I'm going to put the least electronegative atom in the center that can form more than 1 bond. So I put the carbon in the center. I didn't choose hydrogens because the hydrogens only like to form 1 bond. Okay, so I put the 2 hydrogens on there. We have oxygen. Oxygen is going to be bonded to the carbon before it. So I'm going to put oxygen in here. So here's a possible Lewis structure. Let's count up my number of valence electrons. So I have 2 hydrogens in my structure. Okay, I have 1 carbon atom in my structure, and I have 1 oxygen atom in my structure. Now if I look at hydrogen, since I have 1 valence electron in each hydrogen, but there's 2 of them, I have a total of 2 valence electrons from the hydrogens. And since I have a carbon, there's 4 valence electrons for carbons, and there's only 1 carbon, so there's 4 valence electrons from the carbons. And then oxygen has 6 valence electrons. Since there's only 1 oxygen, I have 6 from that one. Okay, so I have 10, 12 valence electrons to build my structure out of. Okay, let's see how many I've used so far with the single bonds. So I've used 1, 2, 3, 4, 5, 6 valence electrons so far. Okay. If I subtract that, I still have 6 valence electrons to find a home for. So let's think about where it could be. Now, if I have all these extra electrons, it's a good idea to try to put extra electrons on the outer, more electronegative atom. So let's go ahead and put that on oxygen. So we put oxygen on there. Let's go ahead and try giving it 3 lone pairs, so a total of 6 electrons. That would be all my electrons at that point. So oxygen has a full octet, but I want you to notice there's a problem. Carbon does not have a full octet at this point. In fact, it only has 1, 2, 3, 4, 5, 6 electrons around it. So if you don't have enough electrons to give everyone a lone pair until you fill their octets, you're going to have to share some and get some multiple bonds. So I want to take one of these lone pairs that I added, and I want to go ahead and move it to put a double bond. So now I put a double bond between the carbon and the oxygen. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've used all 12 valence electrons. And we have a full octet around the oxygen, a full octet around the carbon, and both the hydrogens have 2 electrons around them in their single bonds. So this would be a very stable predicted Lewis structure. So there's my Lewis structure for formaldehyde. Okay. Let's consider the Lewis structure for acetic acid. Now, acetic acid, remember there's a hint about the structure with the formula, how it's written here. So I'm going to go ahead and put the first carbon, and as I showed you before, I have the 3 hydrogens bonded to the first carbon. And then the second carbon's bonded to the first. We're going to go ahead and bond the oxygen next. And the second oxygen, so these 2 oxygens are bonded to that carbon before them. And then the hydrogen's bonded to the oxygen before it. So one of these oxygens I'm going to decide to put a hydrogen on. Okay, so there's a good skeletal structure. Let's count how many valence electrons I have to build my structure out of. Now there's 2 carbons. Make sure you count them all up. So there's 2 carbons in the structure. There's 3 and then another hydrogen, 4 hydrogens total. Count them all up everywhere in the formula. And then there's 2 oxygens in the structure. So if I count my number of valence electrons I have in each of these cases, I have 4 valence electrons for each carbon. I have 1 valence electron for each hydrogen. And I have 6 valence electrons for each oxygen. So I take the 2 times 4 for my valence electrons for the carbon. I get a total of 8 valence electrons for the carbons. Okay. I have my 4 hydrogens times 1 valence electron each. There's 4 valence electrons then for all the hydrogens. And I have my 6 valence electrons for each oxygen, but there's 2 of those, so I get 12. So there's 12 valence electrons for all the oxygens. And so if I look at this, I have 8 plus 12 is 20, plus 4 is 24. So I have 24 valence electrons to build my structure out of. Let's see how many we've used so far with the single bonds we showed in the skeletal structure. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 valence electrons that I've used so far. So I actually still have 10 more valence electrons to find homes for. What I should go ahead then and do is find my electronegative atoms, like oxygen in this case, and put extra lone pairs on the oxygen until they have a full octet. So let's try that. So I'm going to go ahead and put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons on the oxygens to get lone pairs. So I'm going to go ahead and have a lone pair here, here, here on this oxygen. Sorry, covered up that 1 electron. And a lone pair here and here on this oxygen. There was all of my 10 electrons. We notice that each of the oxygens have a full octet, right? And if we look at the carbons, though, this central carbon doesn't have a full octet. This carbon does, so this would not be the best structure as written. Since this carbon has a full octet, we can come up with a better structure potentially. Since I don't have any more electrons to place, though, we're going to have to borrow a pair of electrons from one of the lone pairs. Now, I could try to borrow it from this oxygen's lone pair, but remember I told you oxygen is expected to probably want 2 single bonds or a double bond. So if I were to actually move a lone pair down to form a double bond, I'd have a double bond and a single bond. We predict that not to be a good choice here. In more advanced courses, we would determine what are called formal charges, which would also help us predict that that would not be a good choice. So I'm going to leave those lone pairs alone. Since oxygen can have a double bond, let's go ahead and take one of the lone pairs from this top oxygen. So let's go ahead and clean our structure up a little bit here. Let's take one of these lone pairs and move it down to put it into a double bond. And so at this point we have a double bond to this carbon, and now we have a full octet around this carbon. So we have a full octet around each of the oxygens and each of the carbons, and the hydrogens have 2 valence electrons each. So this is a better Lewis structure than the one we had drawn before. So this would be the correct answer for an assignment for a Lewis structure. Okay. Let's consider hydrogen cyanide. Now, hydrogen cyanide in water would be called hydrocyanic acid. So let's go ahead and look at the structure of this compound. So for a skeletal structure, I'm going to try putting the carbon in the center and a single bond to a hydrogen. And then I'm going to put nitrogen on the outside. Carbon's going to be a good choice for the center. It's the least electronegative other than hydrogen. And so I must have at least a single bond to the hydrogen and a single bond to a nitrogen, but I haven't used all my valence electrons. So let's count how many we had. So for hydrogen, we had one valence electron. And we only had one hydrogen. We have one carbon, one nitrogen. Carbon has 4 valence electrons. Nitrogen has a total of 5 valence electrons. So if I add these all up, we'll see we have a total, in this case, of 10 valence electrons to build our structure out of. And so far I've used 1, 2, 3, 4. So I've only used 4 of my valence electrons so far. So I'm going to take 10, subtract 4 valence electrons, and then I end up seeing that I would have 6 valence electrons to place in my structure. Now, we could put them on the carbon or the nitrogen, but remember we want to put the lone pairs on the more electronegative atom, usually on the outside first. I don't choose hydrogen or it has a full duet. It doesn't want any more. So don't put lone pairs on hydrogens. So I'm going to go ahead and try to fill the valence shell on the nitrogen. So let's go ahead and fill the valence shell. Okay, so I'm going to put lone pairs on this nitrogen and see how many I've used. So I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've used all of our valence electrons. So are we happy with this structure? Let's think if we are. Well, the nitrogen has a full octet, but the carbon does not. So maybe we can come up with a better structure with both carbon and nitrogen have a full octet. Now, in order to do that, though, I'm going to have to move some of these lone pairs on the more electronegative nitrogen down into multiple bonds. So why don't I go ahead and do that? Now, since carbon needs 2 more pairs of electrons, I'm going to take 2 of the lone pairs rather than just 1. Okay, so let's take 2 of the lone pairs here and move those down to multiple bonds. So if I put a triple bond between the nitrogen and the carbon, and as you recall, these are potential sets of bonds we expect to have on these species, we could end up having a full octet around the nitrogen, a full octet around the carbon, and the hydrogen has 2. So this would be a good structure to report as our answer. Okay. Let's consider some polyatomic ions for our last examples in this video. So let's look at the perchlorate anion. The perchlorate ion has a -1 charge. Now that's going to be important when we draw its Lewis structure. We're going to have to correct for that negative charge, that extra electron that we had gained. But first of all, let's go ahead and draw our Lewis structure. I'm going to put chlorine in the center, and then we have 4 options. So let's put them symmetrically on the outside of our structure. 1, 2, 3, 4. And if we predict that we have at least a single bond between the chlorines and each of the oxygens, we might have this as a skeletal structure. Let's go ahead and count how many valence electrons I have, though. So I have 1 chlorine, right? And it has a total of 7 valence electrons. And we have 4 oxygens, right? And the oxygens have 6 valence electrons each. So all the valence electrons I have from chlorine, since there's only one of them, is 7. And since I have 6 electrons for every oxygen, and I have 4, I'm going to have 6, 12, 18, 24, right? 24 valence electrons from the oxygens. If I were to add these up right now, I'd end up with having 31 electrons. That would be an odd number. Now, an odd number of electrons we normally won't have unless we have something like a free radical, where something has an incomplete octet. However, we've forgotten one thing so far with this table. We forgot the charge. So since I have a -1 charge here, I have 1 extra electron that we need to add to our total, because we've gained 1 more to get that negative charge versus what we had in our valence shell. So I add 1 more electron to the total for that -1 charge shown for the polyatomic ion. So if I add that in, we're going to go ahead and see what we have: 32 valence electrons in our structure. Okay, so if I have extra electrons that I need to place, I'm going to put them on the outer atoms. And I haven't used them all up so far. 1, 2, 3, 4, 5, 6, 7, 8. I've only used 8 valence electrons so far. So let's go ahead and try to fill the octet of the outer oxygens, the more electronegative atoms. So I give each of the oxygens, let's say, 3 lone pairs for this perchlorate ion. Now, so far I have 8 around this oxygen, a full octet, so there's 8, then 8 whoops, I need another lone pair, and 8 around this one, so that would be 16, and then 24 for this option, and the last one's going to give me 32. So there's all 32 valence electrons, and the chlorine has a full octet because of the 3 single bonds. So far we've completed the octet here. So are we done with this structure? Remember, for polyatomic ions, we need to show square brackets around them. So for the perchlorate, I'm going to go ahead and put square brackets around the ion, and in the upper right hand superscript I will show my charge. So the perchlorate ion has a -1 charge. Okay, so that would be my answer for this one. Let's go ahead and look at one more anion. Okay, so when I look at the nitrate ion, well, I'm going to go ahead and put nitrogen in the center, the least electronegative of the atoms. I'm going to put oxygens on the outside here, and single bonds to them. So there's my skeletal structure. I have 1 nitrogen in my structure, and I have 3 oxygens in my structure. There's 5 valence electrons for each nitrogen, and there's 6 valence electrons for each oxygen. So I have here 5 for the nitrate, or nitrogen and nitrate, 6 for the oxygen. Since there's 3, I have 6, 12, 18. Now if I added those up, I'd have an odd number. That tells me to maybe think about this for a second. I forgot to add in the charge. Since I have a -1 charge, I need to add 1 more valence electron. If I add these all up, we're going to go ahead and find then that we should have 24 electrons to build my structure out of. We can go ahead and put those on the outer options. Let's do so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 for the single bonds, and so we end up having all 24 electrons used. Are we happy with this structure? There are several reasons we are not. In fact, there's at least 3 reasons. If we look at this, we can see that the nitrogen in the center does not have a full octet. So we're going to go ahead and have to take a lone pair in the structure and remove one of the lone pairs of electrons, the non-bonding pairs of electrons, and move it down into a multiple bond. Now, a big question here is which one of these oxygens should have a double bond? In our next discussion, we'll be looking at resonance structures and resonance hybrids, and we'll discuss that in greater detail. Right now, let's just pick one of the options until we get to that point in our discussions, and that's going to be our potential structure. The next thing we need is, since it's a polyatomic ion, I need square brackets around the polyatomic ion, and in the upper right-hand corner, we should show the charge. It's a -1 charge. Okay. So let's go ahead and look at a cation. So let's look at the polyatomic cation, the ammonium cation. If we look at the ammonium cation with respect to drawing our Lewis electron dot structure, we can go ahead and put nitrogen in the center. Remember, hydrogens we're going to put on the outside. There's 4 of them. Go ahead and add up the number of valence electrons if you'd like to on your own this time. But if my skeletal structure has a single bond to each of the hydrogens, we're going to go ahead and find 1, 2, 3, 4, 5, 6, 7, 8 electrons I've used so far. Now, the nitrogen has 5 valence electrons. And there's only 1 of them, so I just have a total of 5 valence electrons from that 1 nitrogen. And then I have 4 hydrogens with 1 valence electron each. So there's a total of 4. However, I need to remember this is a polyatomic ion, so I have to account for the charge. Now, there's a positive charge, so we have to treat this in a different manner. It's lost an electron. So since I have a positive charge, I need to subtract a -1 electron from my total. So that leaves me 5 plus 4 minus 1. So we only have 8 valence electrons to build my structure out of, and that's exactly how many we've used. So we're actually done with the structure, other than we need to show square brackets around the cation, the polyatomic cation, and show the positive charge in the upper right-hand corner. Okay. Now, for our very last Lewis structure, I thought I'd show you a situation where we have brackets in my chemical formula. So here we have acetone. Now, acetone is a very popular component in fingernail polish remover. Okay, so in this case, when we're looking at the acetone, we have 2 repeating groups. We have CH3 twice in the structure. That's what this means with the brackets. It means this 2 affects everything inside the brackets. So we have 6 hydrogens and 2 carbons in this part of the structure. Then I have another carbon and an oxygen. So let's try using this carbon here as my central atom in my skeletal structure. So I'm going to put that in the center. I'm going to show an oxygen in the center. And I have 2 CH3 groups. Now you notice when you see a CH3 group, those are often at the ends of the molecule. So why don't we show a CH3 group in one position and a CH3 group in another position with the 3 hydrogens. The second CH3 group we're going to go ahead and show here with its 3 hydrogens bonded to it. And we can put a bond to this oxygen. Now if I go ahead and count my total number of valence electrons, well, there's a total here of 3 carbons, 6 hydrogens, and 1 oxygen. So there's 4 valence electrons for each one of my carbons. So I have a total here of 12 valence electrons for all the carbons. Plus I have 1 valence electron for each hydrogen, and there's 6 of those. So there's a total here of 6 electrons, valence electrons for all the carbons. Oxygen has 6 valence electrons. There's 1 of them. So I have a total of 6 here. If I add these up, I have 12 plus 6 is 18, plus 6 again is 24 valence electrons. Okay, if I look at my structure, I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've only used 18 valence electrons so far. So let's subtract that from the total. I still have 6 electrons to find locations for. Now I could put that on the very electronegative oxygen, right? I could put 1, 2, 3, 4, 5, 6. I would take care of the 6, but this carbon wouldn't have a full octet. So it actually would be better to take one of those lone pairs and remove it from the oxygen, move it down to a double bond. So we're still using the same 6, but now they're present in a double bond here rather than as a lone pair for those extra 2 I just removed. So I go ahead and show, in this case, a double bond. Now this carbon has a full octet. Each of these carbons have a full octet, and that oxygen has an octet as well. A double bond and 2 lone pairs. Okay, that uses all 24 electrons if you'd like to count that up. So that would be my final answer in this case. Okay, so go ahead and make sure you're working on the homework for the chapter, and please ask questions if you have any. Okay, have a great day, everybody.